Hello everyone, I'm Paul and today we're solving problem 3539. Find sum of array product of magical sequences. Here it says this is hard, and believe me, this is very hard, or at least it was for me. So next I will show you how to solve this efficiently step by step. The first challenge here is to understand what's happening here. We are given two integers, m and k, and an integer array nums. And we need to find magical sequences. And here we have the conditions for a magical sequence. It has a size of m, and it's built with indices from the array nums, and this is a hard one. The binary representation of 2 to the power of every value in the sequence has exactly k set bits, meaning bits that are 1. Once we have a magical sequence, we can get the array product of this sequence by taking the product of nums at every value in the sequence. And our job is to return the sum of the array products for all valid magical sequences, and we need to return it modulo 10 to the power of 9 plus 7. So as you can see, there's a lot going on here. So let's see a few examples. Let's say we have this. So we need to find magical sequences of length 1, and given that the size for this is 1, we only have one possible sequence. Now we need to check if this is magical or not. We know that k is 1. So here our sequence has only number 0. Remember that sequences are built with indices. So we only can take index 0. So this is the only sequence we can take. Now remember how we build binary numbers. For position 0, we have 2 to the power of 0. For position 1, 2 to the power of 1, and so on. So let's say we want to transform number 3 in base 10 to binary. Well, we need 1, 2 to the power of 1, and 1, 2 to the power of 0. So this is 3 in binary. Now let's say we want to get 2 in binary. We only need 1, 2 to the power of 1. So this is 2 in binary. Now we only have one element in this sequence, which is 0. So we do 2 to the power of 0, and the result is 1. And this number has exactly one set bit, and k is 1. So this means we have a magical sequence. This is a magical sequence. So now we can add to the result nums at 0, meaning 28. So we return 28 here. Now let's say we have this input. So we need to find sequences of length 2. So for example, let's say we take the sequence 0, 1. And we will have a mask, which is initially 0. And now we are checking this. So 2 to the power of 0 is 1. So our mask is currently 1. And next we continue here. 2 to the power of 1 is 2, which is this in binary. So here we can add 2 to the mask. And the result for this is 3, which is 1, 1 in binary. We need 1, 2 to the power of 1, and 1, 2 to the power of 0. Okay? So this is 3 in base 10. And here we have 2 set bits, and k is 2. So this is a magical sequence. So we can add to the result nums at 0 times nums at 1. And 3 times 2 is 6, so we add 6. And we can try this sequence also, 1, 0. So first we are checking this. 2 to the power of 1 is this in binary. The mask is 2, and we can add 2 to the power of 0, which is 1 in base 10. This is 3, and we know that in binary this is 1, 1. So we got the same result. Here we have 2 set bits, and k is 2, so we have another magical sequence here. So we can add to the result nums at 1 times nums at 0. So 3 times 2 is 6. So we add another 6 here and the result is 12. And it's very important to remember that we can repeat elements in the sequence. So let's say we take 0, 0. And 2 to the power of 0 is 1. And if we do 1 plus 1, this is 2. And 2 in binary is this. And here we have only one set bit. And 1 is different from 2. So this is not a magical sequence. And if we try the sequence 1, 1, 2 to the power of 1 is this in binary. And if we add 2 to the power of 1, the result is 4. Meaning 1, 2 to the power of 2. So this is 4 in binary, and here we only have one set bit, and 1 is different from 2, so this is not a magical sequence. Now we have tried every possible sequence, so we return the result 12. So as you can see, when we have different values in the sequence, we have an amount of set bits corresponding to the amount of elements in the sequence. And if we have one or more equal elements, well, in this case we have different set bits. Here you can see the example. And that's why we need to keep track of these bits. And for this we are using a mask. So keep this in mind. Let's say we have the same input, but k is 1 this time. So we are looking for sequences of length 2. We can try 0, 0, and 2 to the power of 0 is 1. If we add 2 to the power of 0, the result is 2, which is this in binary. Here we only have one set bit and 1 is equal to k, so this is a valid magical sequence. So we can add to the result nums at 0 times nums at 0. So we add 3 times 3, meaning 9. Now let's say we try the sequence 1, 1. So 2 to the power of 1 is this in binary. 2 to the power of 1 is 2. And if we add 2, the result is 4. 4 in binary is this. Here we only have one set bit. K is 1, so this is another valid magical sequence. So we do nums at 1 times nums at 1. 2 times 2 is 4, so we add 4 here. And the result is 13 because these are the only magical sequences in this case. So with this, I think you get the idea, or at least now you know what the problem is asking. Now the question is, how can we solve this? Now let's say this is a valid sequence, and remember that we can repeat values in sequences. So let's say that here we have 2 repeated values, 1 unique value and another unique value. So we have 4 values in total. Now the question is, where can we put these 2 repeated values? Well, we can use this here and here, or here and here, or here and here, or here and here, and so on. And in case you have never seen something like this is something called combinatorics. And there's a well-known formula for this which goes like this. NCR is n factorial divided by r factorial times n minus r factorial. In this case, r is 2 and n is 4. So we are looking for combinations of 2 in 4. So we do this is equal to 4 factorial divided by 2 factorial times 4 minus 2 factorial. The result for this is 6. And let's see what this means here. We have one combination with these 2 elements, another one with these 2, 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 And finally, another one with these 2 elements. So here we have 1, 2, 3, 4, 5, 6 combinations. These 6 combinations. So from a valid magical sequence with 2 repeated elements, we can take 6 magical sequences. Okay, so this is very important and this is the formula. So let's go with the approach now. Let's say we have the same input as before and we are iterating this from left to right. So first we are here and we have a few choices. We can take 0 instances of this element. We can take 1 index 0 or we can take 2 index 0. And this is it. We can take up to 2 of these values because m is 2. We are building sequences of 2. So for example, if we decide to take 0 index 0, next we can take 0, 1 or 2 of this. So we have 3 more choices. Here we have 3 more choices. Here we have 3 more choices. So here you can see how this is a dynamic programming problem. Now we need to carry a state with us, and this is the state. We have a mask. Here we are keeping track of the binary representation of the mask, and m is initially 2. These are the remaining elements to fill a sequence. So initially we need to fill 2. K is our target. So if at any point the amount of bits in our mask, the amount of set bits, meaning bits that are 1, is equal to our target, which is 1 in this case, and we have a full sequence, meaning m is equal to 0, this is a successful base case. Here we can return 1. We start from index 0, so we start from here. And if at any point this is not true and m is 0, meaning we have a full sequence, or we reach the end of this array, meaning I is equal to length of n, this is a non-successful base case. In this case, we return 0. So let's see what happens if we choose to take 0 instances of this element. Well, the mask will still be 0. We are adding the frequency to the mask every time. 0 plus 0 is 0. M is still 2. K is still 1. And now we are moving to index I plus 1, meaning 1. And just to be clear, this is for a frequency of 0. Now let's see what happens when we have a frequency of 1. This is the initial mask. We start from 0 and we add the frequency of 1. So the new mask is 1 in base 10 and this is 1 in binary. And here we are using 0. Why? Well, because here the target k is 1 and the least significant bit in our mask is 1. So we can right shift this, and this means we are popping this and the mask is 0 again, and we can reduce 1 from our target k. That's why here we have a 0. So our new mask will be 0. We are right shifting this, and the new k will also be 0. M will be the previous m minus 1 because the current frequency is 1, so we subtract 1. And I will be the previous I plus 1. We are moving 1 index. Now let's try a frequency of 2. Let's see what this means. We have a mask that's 0. We add a frequency of 2. So the new mask is 2. 2 in binary is this. And here the least significant bit is 0. This means that we are repeating an index. Remember, we have a frequency of 2, so we are repeating an index. Let's see what this means. The new mask will be this right shifted, meaning 1. That's why here we have a 1. And the new m will be the previous m minus 2 because we have a frequency of 2. And k is the same. Why? Well, because the least significant bit here is 0. So we keep the same k as before. Our target stays at 1, so here we keep 1. And the new index is this plus 1, meaning 1. And here m is 0, and the amount of bits in the mask is 1, and 1 is equal to k, so we have a successful base case. So at this point we can return 1 here. So now we are back here, and the contribution for this result is nonce at I, meaning 3, and this is to the power of 2, because here we have a frequency of 2, and this is times the result for this branch, meaning 1, times the combination, this is MC2, meaning 2C2, meaning how many combinations do we have of 2 in 2? This is 1. The result for this is 3 times 3, meaning 9. So we add 9 to the result. Now if we continue with this branch, here we have an unsuccessful base case because this is a 2, here we reach the end of the array. Here we have another unsuccessful base case, so here and here we return 0. And here we have a successful case because m is 0 and the amount of bits and the amount of set bits here is 1, and 1 is equal to the target k at this point, which is also 1, so we return 1. So let's see this contribution here. We are at index 1, meaning we are at this element, and we are taking 2 instances of this element, so we are doing 2 to the power of 2, and this is times the result for this branch, meaning 1, and this is times the combination of 2 in 2. So this is 2C2 and the result is 1. So the final result for this is 4. So here we have a 4. So now we need to see what's the contribution for this up here. And well, here I is 0, so we are standing here. So we do 3 to the power of the current frequency, which is 0, and this to the power of 0 is 1. And this is times the result here, which is 4, times the combination of MC0. And 2C0 is 1. So this is 1 times 4 times 1, which is 4. So we add 4 to the result. And 9 plus 4 is 13. And this has 3 different branches which will return 0 each. So this will return 0, and this won't contribute anything to the result. So finally we can return 13. So as you can see, there's a lot going on here. This is a really hard problem. So I recommend you to take this step by step. And with this approach in mind, let's go with the code. First we say mod is 10 to the power of 9 plus 7. And now we can build our function. We are calling this dp. And remember, we have to carry 4 variables with us: mask, m, k, and index. Remember that this k is the target k. So when the amount of bits in the mask, the amount of bits that are 1 is equal to the target k, we have a successful case. So first, for the successful case, if m is 0 and mask.bit count is equal to k, we just return 1. Now for the unsuccessful case, if m is 0, meaning we don't have any spaces available for the current sequence, and this is not true, or we are out of bounds, meaning is the length of nums, we just return 0. Okay, this is the unsuccessful base case. Now, total is initially 0, and first we can add the scenario in which we skip the current index. And this is dp, and we take the current mask every time we right shift the mask by 1. And we keep m as it is because we are skipping this element. We still have m available elements for this sequence. And now if the least significant bit in the current mask is a 1, we want to subtract 1 from the current k. If it's a 0, we want to keep k as it is. So how can we do this? Well, we say k minus mask bitwise and 1, and we are moving to the next index, so I plus 1. And just in case, we mod this by mod. So now we have more scenarios for each frequency in the range of the available spaces for the current sequence. So for frequency in range from 1 to m plus 1, remember m is included and this is non-inclusive, so we add 1. The new mask will be mask plus frequency, and the next scenario will be dp with the new mask right shift 1, and we are subtracting from our available elements for the current sequence the current frequency. And for k we do the same as before. If the least significant bit in the new mask is a 1, we need to subtract 1 from the target k. So k minus new mask bitwise and 1, and we are moving to the next index, and this is modulo mod. And now we can add to total. First we add the current number. Remember that we can have repeated values, that's why we have a frequency. So we need to add nums at the current index to the power of the current frequency, and we mod this by mod. So this is pow, and this is times the result for the next scenario. Just to be clear, here we do the current element times next element. Remember that we need to get the product of the sequence, meaning nums at every element in the sequence. Okay, so and here we need to do this times MC frequency, because if we have repeated elements, remember that we can have different combinations for these repeated elements. So here we can use this in Python comp, and this is MC frequency. And just to be clear, here we add combinations of frequency in M. This is the current frequency, and this is modulo mod. Here we can return total, and finally we can return this is dp, and we start with 0 as mask, m, k, and from index 0, and this is modulo mod. So this is the entire code. Now let's submit this and see if it works. Here I'm missing a very important part, and is that we need to cache the result for every combination of mask m, k, and I, because we can have repeated scenarios. So we need to avoid duplicate work. That's why we need to cache this. So let's try again. As you can see, this works and it's very efficient. Here, time complexity will be time is big O of mask can grow up to m, so this is m times m times m for this loop, so this is m times k times, we will say that n is the length of nums. So this is m to the power of 3 times k times n, and space will be big O of m to the power of 2, because let's say this is m, this is also m, so this is m to the power of 2 times k times n, and this is the space for our cache, so this is overall space complexity. So this is the entire code. I know this is a lot. This is a really hard problem, or at least it was very difficult for me. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.